Hey guys, this is the academic chemistry video for chapter 2, section 4, part 2, chemical versus physical changes. And today we're going to talk about the energy that is associated with any kind of change, whether that's chemical or physical. All right, so first, when I talk about energy, we need to kind of define it. So there's two main types of energy that you want to think about here. The first is chemical energy. So chemical energy is energy that's stored in the bonds that hold atoms together. Atoms don't really want to be together, so there has to be some sort of energy or some sort of resource that pulls them together, and it depends on what type of bond it is, how much energy there is. Now, I don't expect you to be able to calculate the amount of energy. You just need to understand that some bonds have more energy than other bonds. So as you can see here, this bond between hydrogen and oxygen, there is only one bond between them. It's called a single bond. We'll learn about that later in the year. And this has 111,000 calories per mole versus double bond shown here between carbon and oxygen. This has 192,000 calories per mole. So this is a stronger bond. It takes more energy to have this bond in your molecule. The other type of energy is kinetic energy. And kinetic energy measures the movement of molecules. So if molecules are moving faster, then they have more energy. So for example, a gas has more energy because molecules are moving faster than a liquid, and that has more energy than a solid. So every time you go from a solid to a liquid, that substance gained energy because it's moving around faster. Every time you go from a liquid to a gas, so liquids are kind of doing this, like moving around, versus gases are like, woo, they're crazy. So which has more energy, just kind of moving, or this one has more energy, it's moving around more. When you think about energy, there's a few things I want you to kind of think in the back of your head. So energy can be measured in joules, it can be measured in calories. You've probably heard of that when you think about like how many calories are in something you're eating. It's how much energy is in it. Or in degrees Celsius. Now these aren't all real ways of measuring energy. Really, joules is the only way, but calories and degrees Celsius are things that are more familiar to you, and you can kind of relate them back to energy. All right, so there are two types of energy changes in reactions, and that's both physical and chemical. And the first one is an exothermic reaction. So an exothermic reaction is when the change causes energy to leave the system. So think of exiting. Energy is leaving the system or exiting the system. These reactions feel hot outside the system. So if you mix something up in a beaker, and when you mix it, suddenly it gets really, really, really hot, and that's an exothermic reaction. Anytime anything explodes, that's called a combustion reaction. Those are always exothermic. They're releasing a ton of energy. You also had an exothermic reaction in the stations lab when you had calcium chloride and you put it in water and then you squished them. You felt that heat come off. That's an exothermic reaction. The product had less energy than the stuff before it, so that energy that was stored in the bonds were released and you could feel it. In exothermic reactions, energy in the bonds are lower than the products of the reactions. So here describes a reaction going forward. So here's when you're starting. So these are your products. I'm sorry, your reactants. And then you go forward, these are your products. If you notice, this is the energy stored. So you have a certain amount to start, the reaction happens, and then you have less energy in the end. Well, energy can't be created or destroyed. So since there's less energy inside the system, so your products have less energy than the reactants did, it had to be lost and it left. And that that feeling is heat. So that's how you're really going to tell this. Exothermics feel hot on the outside because there's less energy on the inside. The energy had to go somewhere. If you're holding that beaker where you did the reaction, the energy went into your hands. All right, the other type of reaction is an endothermic reaction. So an endothermic reaction is when the change causes energy to enter the system. So it pulls energy into the system. Now, these reactions feel cold, and I'm going to say they feel cold because we're used to saying the word cold, but cold isn't actually a thing in science. So the thing is, there's no such thing as cold, there's only the lack of heat. Whenever anything feels cold to you, it's because energy is being sucked out of you and brought to whatever feels cold. So right now, if you're sitting at a desk at school, I want you to put your hands down on the desk or on the metal part of the desk. And you're going to say, wow, that feels cold. Well, it's not really cold. It's that your hand has more energy And then the chair or the piece of metal or whatever you're touching is taking that energy, and losing energy feels cold. So whenever anything feels cold, it's because the thing you're touching is pulling energy from your body. If energy is entering into a system, it feels cold because it's literally pulling energy from your hand. So energy in bonds are higher in the products than in the reactants. So if you look at this, your reactants here have a certain amount of energy. Now this number here is very arbitrary. It's not saying a certain amount, like I could have drawn it down here or right here. But the fact is, our reactants have this amount of energy. The reaction happens, and then here's the energy of the product. Notice it has more energy. Well, where did that energy come from? It came from the surrounding area. So it had to suck in energy from whatever was around it, and that's why it feels cold, because it takes away energy from you. Here's a nice little graphic I like to just kind of think about what's happening with the energy. So in an exothermic reaction, exo, think of energy leaving. And look, energy is literally coming out of this Erlenmeyer flask. And that's why it feels heat on the outside. Heat is going out. For an endothermic reaction, though, it's taking heat in. So heat is coming in or entering, and it feels cold because if heat is entering the beaker, it's not entering your hands, so it feels cold to you. So this is going to feel colder than the surroundings. All right, let's go through a few examples. So here are 3 examples, and I want you to decide, do you think that they are endothermic or exothermic? So exothermic means energy was released. Endothermic means energy is taken in. I want you to be able to support this, so think of why you think it is. Go ahead and pause the video, and when we come back, I'll go through all the answers and explain them. All right, hope you paused the video. So burning wood. Burning wood, anytime anything is on fire, anytime any explosion, it's always releasing energy. That's always going to feel hot. So that's an exothermic reaction. Photosynthesis, you've gone over this in biology. So that's when plants take in the energy from the sun. So since they are taking in energy, notice energy is a reactant. If energy is being taken in, then it is endothermic. How about boiling water? So when you boil water, you're going from liquid to gas. Gases have a higher state of energy because they're moving around really fast. So since they have a higher energy, energy had to be taken in, and so this is endothermic. Another one to think about, sometimes the state of matter ones get confusing. A totally separate example is why Eskimos build igloos. So when water freezes, it's going to go to a lower state of energy, so liquid to solid, right? Solids are lower energy, so that energy actually gets released to the surroundings, which is why making an igloo is really beneficial for Eskimos for helping to stay warm. So if you get confused, think of why would an Eskimo make an igloo? Well, they want to get warm, so going from a liquid to a solid, freezing, releases energy, or exothermic, and then you can kind of think, is it like that or the opposite? So I hope this helps. Make sure you ask questions if you have any, and good luck on the rest of the section.